In this video, we will use Newton's second law to solve a problem involving a skier making a jump. And for the first part of this problem, we will deal with her trip up. The problem says a skier approaches a ramp at a speed of 17 meters per second. The ramp is 7.25 meters long at an angle of 15 degrees. The coefficient of kinetic friction between her skis and the snow is 0.185. We can neglect air resistance. And we're asked, first, how fast is she traveling when she leaves the ramp and at what angle? And how high is she from the ground when she takes off? All right, well, first, we always draw a diagram showing the information we're given and the forces acting on the object. So, here we have our skier. Notice it is not a very steep ramp here, 15 degrees. We have the length of the ramp, 7.25 meters. We have our starting velocity, 17.0 meters per second, and our final velocity when she reaches the top, which we do not know. And the angle of the ramp is 15 degrees. Now we want to draw the forces which are acting on the skier. Of course, we have the weight force, mg, which is always straight down. Here we have the normal force, Fn, which is always perpendicular to the surface of the ramp. And we have the friction force. Notice that the direction of the friction force is down the ramp because the motion is up the ramp, and the friction force always opposes motion. Now, in our search to find the final velocity, we're going to be using the third kinematics equation here. And we know the initial velocity, 17 meters per second. We know the displacement, 7.25 meters. So if we're going to find this final velocity, we need to find the acceleration. But we can do that using Newton's second law. So there's our setup. Next, step 2, we choose a coordinate system. And as we have done in the past with inclined surfaces, we're going to define the x and y axes a little bit differently by saying that the x-axis is parallel to the ramp, so the positive x direction is up the ramp, and the y direction is perpendicular to that, so the y direction is perpendicular to the ramp. By twisting the coordinate system like that, it's going to save us a lot of trouble. Now with this coordinate system, the acceleration of the skier is going to be down the ramp, and that's going to be in the x direction, the way that we've defined it. And the way we've defined the y direction, her acceleration in the y direction is going to be 0 because she is not rising up off the ramp, nor is she sinking down into it. So from the y direction, her acceleration is 0. And we're concerned with what her acceleration is in the x direction. Notice how that acceleration is going to be down the ramp, since she's going to slow down as she goes up the ramp, so acceleration and velocity should have different directions. Now, the next question we ask, step 3, given this coordinate system, are there any forces that need to be broken up into components? If so, draw those components and write out formulas. Well, the way we have defined the x and y axes saves us a lot of time because we don't have to break the normal force up into components, it's in the y direction. We don't have to break up the friction force into components, it's in the negative x direction. And we don't have to worry about components for the acceleration. The only force that needs to be broken up into components is the weight force, and we can do that as we have done so many times, like so. making sure that x and y are at right angles to each other, And this angle right here is going to be 15 degrees, the same as the angle of the incline. Well, now, since these two components and the weight force itself form a right triangle, we can use the trigonometric functions to find the components. Beginning with the sine function, the sine of 15 equals opposite over hypotenuse. Well, opposite this 15-degree angle, we have Wx, and the hypotenuse is the weight force, mg. Solving this equation for Wx, this is what we get for the x component. Now, to find a formula for the y component, we use the cosine function. Cosine of 15 is adjacent over hypotenuse. And we see here that wy is adjacent to the 15-degree angle. And the hypotenuse is once again the weight force mg. And so the y component of the weight force is going to be mg cosine 15. So we've completed step 3. We only need to break one force up into components, and we've written out formulas for those components. And then finally, we utilize Newton's second law to figure out what we need to find, which is the acceleration in the x direction. So, of course, we first look at Newton's second law for the forces in the x direction, but you should always write out both equations in case you need them. So let's look first at the forces in the x direction so we can find the acceleration in the x direction. There are two forces in the x direction, and as we've defined it, they are both in the negative x direction. So adding them together, we would say negative Wx minus Fr equals mass times acceleration in the x direction. We have a formula for Wx, and we have a formula for the friction force, which is the coefficient of friction, mu k, times the normal force. Once again, this has become a challenge to find the normal force, so we can then find the friction force. So to find the normal force, we turn to the second of Newton's second law equations for the y direction. There are two forces in the y direction, and they're in opposite directions, Fn being positive and the y component of the weight force being negative. So when we add them up, we actually subtract them. Now, the acceleration in the y direction is 0. So the sum of the forces in the y direction is 0. And this can only be true if Fn equals Wy, which, as we can see up here, is mg cosine 15. So now we have a formula for the normal force that we can plug in to here. The formula for the x component of the weight force is mg sine 15. And the formula for the normal force, which is the y component of the weight force, is mg cosine 15. And that's equal to the mass times the acceleration in the x direction. As has happened so many times before, we notice that the mass cancels out. So the mass is irrelevant in this situation, making the acceleration in the x direction minus g times the sine of 15 minus mu k times g times the cosine of 15. And calculating that out, we get minus 4.29 meters per second squared. Notice the acceleration is negative, once again, because it is opposing motion in the negative x direction. So our acceleration is negative because we are slowing down. With that acceleration in hand, we can now go to the kinematics equation. V final squared equals V naught squared plus 2 times A times the displacement. All right, and now we plug in the values. V naught is not 0. Remember, this time it's 17 plus 2 times negative 4.29. That negative sign is very important. Times the displacement, 7.25. Well, you calculate all this out, and we get a value for V final squared of 226.79, which gives us a V final of 15.1 meters per second. So, as she goes up the ramp, her velocity decreases from 17.0 meters per second to 15.1 meters per second. And so the final velocity when she flies off the ramp is 15.1 meters per second at 15 degrees to the horizontal. Now, we're not quite done yet, because the question also asks us, how high is she from the ground when she takes off? Well, that is a simple matter of applying some trigonometry to the ramp itself. If we just draw the ramp now without anything else, we can see that the ramp has an angle of 15 degrees and a length of 7.25 meters. And this right here is the height that we want. Well, we go to the sine function. The sine of 15 degrees is opposite over hypotenuse, right? And that's going to be h is opposite the 15-degree angle, and the hypotenuse is 7.25. Solving the equation for h, we get that the height is 7.25 times the sine of 15 degrees, and that works out to be 1.88 meters. So when she leaves the ramp, she is traveling at a speed of 15.1 meters per second at an angle of 15 degrees to the horizontal, and she is 1.88 meters off the ground. We will now carry this information over into the next video to talk about the trip down.